Hello, everyone. In this lecture, I want to talk about the concept of pairing, one of the preliminary knowledge that we need them to understand closely. Okay, so we want to very quickly overview the concept of group. You remember that it was a set of elements with a binary operation that satisfy four properties. And then in previous lecture, we introduced two groups, G1 and G2, and both of them were a group uh, made of electric curve with the formula y to the power of 2 equals to x to the power of 3 plus x plus 9. And the first group was it was defined over the field f sub 101, and the other group was generated of the extension field f sub 101 squared, right? Then we discussed the generator of a group also and mentioned that the generator of the first group, G1 equals to 4 and 28, and the generator of the other group also is determined, right? Now, in this lecture, we want to introduce another concept in group, and that is the order. For the meaning of order, there are two definitions in the concept of group. The first order of a group, and that is the number of elements in the group. So, for instance, in the first group that we see group G1, we need to count how many elements there are in these sets. And you remember that all of this blue small circle, there were an element in the group, and also another element, the identity element at the infinity, right? So when we count all of these elements, we see that the number of this counting is 119. So then the order of group G1 is 119. And the order of G2 also is a big number. It is over than 10,000, right? Okay. So other than the order of group, we also have the order of an element. So uh, if we want to compute the order of an element, we need to compute n multiplied by the elements, and n is a positive integer, and then to see if the if the result equals to the identity element or not. So remember that the identity element in group G1 and G2 is infinity for this group G1 and G2, right? So this means that if you want to compute the order for this point 21 and 10, we need to do this multiplication, n multiplied by 21 and 10 for different values of n, right? And then see if the result equals to infinity or not, right? Now we want to use our website to see that if this value 7 is correct or not, right? Okay, so let's go back to our website. Okay, here on the ZKP, and then growth, and then elliptic curve cryptography, and computation over FP. So here, right? So the curve is already defined as our defined curve, and then this is the list of 119 points. Now we want to compute n times of 21 and 10, right? So here we write 21 and 10, and we start from 2, so the result is not infinity, right? So 3, not infinity, 4, not, 5, not infinity, 6, not infinity, and 7, infinity, right? So we started from 2, and then we saw that the smallest value that make the result equals to infinity, it is 7, right? So then we say that, okay, the order of this point, point 21 and 10 equals to 7. So If you compute the order for another point like 25 and 2, and then you will see that the order equals to 17. Okay, so this means that the order of different elements in a group might be different from each other, right? So for the other group, we have the same definition. We need to find the smallest value of n to see that if the result of multiplication equals to infinity or not. So the point here equals to 49 and okay, so let's check for this group also. So this is the group G2, and this is so the curve and the field already defined. Now we have this scalar multiplication. So 2 times of 49, and this is 0. The other one is 36 and 83. So this is the result is not infinity. So we increase 3. The result is not infinity. 4, not infinity. And here it says that if you put 85, so 85, so then we see that the result is infinity, right? So this is another symbol that we show infinity in the groups. Okay, so now we compute the order for one element from the group G1 and one element from group G2, and you can check the order for other elements from group G1 and G2. And again, you see that the order of elements in group G2 might be different from each other, right? Okay, after this introduction, we want to discuss the definition of pairing. So pairing, it says that suppose that we have an elliptic curve like E. So we already determined our elliptic curve, right? Y to the power of 2 equals to x to the power of 3 plus x plus 9. This is our curve. So this is our curve. And it is defined over finite field f sub p and f p squared. So, and we have group G1 and group G2, right? So this is group G1 and this is group G2. And there should be another group of GT, which is called G target, the target group. And then pairing is a function that takes one element from group G1 and the other element from group G2 and do some computation over these two elements. So this multiplication, this is not the meaning of multiplication. It is just a symbol, but in practice, it consists of so many computations. So the function do many computation between the elements from group G1 and group G2, and the final result is an element from the target group. Okay, so this means that we have a function, take one element from the group G1 and the other element from group G2, do some computation, and then the result is an element from the target group. So in our example, the target group here is a group that consists of the elements of the extension field, the field that we already introduced in lecture 3. Okay, now the complex part is that uh, we cannot define any kind of function, okay? So in pairing, the functions should satisfy these properties. So the first one, the third, and the fourth. All of these properties should be satisfied, then the function is accepted as a pairing, right? So in this lecture, first we want to follow an algorithm to compute the pairing, and then we'll come back again to these 4 properties to ensure that our defined function really satisfy these four properties. Okay. For example, we want to compute the pairing of 2 points. So similarly, the curve is defined like the previous lecture, and the prime value is 109. And now we want to compute the pairing between these 2 points. So point 4 and 73. Okay, it is 73. Yeah, it should be this one, right? So this is the points 4 and 73, right? So the other point is 92 plus 53i and blah, blah, which is a point from this one, right? So there are so many points that are not shown, and this is a point from that unshown list of points. So 1 point from group G1 and 1 element from group G2 are given to this function, and then their final result is an element from this group. Okay, so the question here is that what is this function, and what are the computation that would be done over these two elements? Now we want to overview the algorithm, the Miller algorithm that is needed to compute the veil pairing and Todd pairing or Tate pairing of these two elements. So this is not a complex algorithm. It is just repetitive, and I will discuss different steps in this algorithm when we are following and overviewing the example. Okay, the algorithm starts with taking 2 points, right? So we already need 2 points, and they are defined already in previous slide. So we mentioned that we want to compute pairing between 0.4 and 73, and also G from the group G2. So then the two elements P and G are given. So the first step is passed. Now we need to compute the torsion, the torsion order n. So what is torsion order n? So the torsion order n equals to the least common multiple between the order of P and the order of Q. So in the introduction of this lecture, we discussed the order of an element, right? The order of the 0.4 and 73, and also the order of this point, right? So again, you can check by the website to see if what is the value of n, that's n multiplied by 4 and 73 equals to infinity. And if you check using the website, you will see that the order for the point P equals to 119. So similarly, the order of point Q also equals to 119. So therefore, the least common multiple between these 219 values equals to 119. So then the value of n, which is the torsion order, equals to 119. Okay, so the next step here is that the computing the value of I, and I equals to the length of the number of bits of n in binary minus 1. So this means that we need to write the n in binary, and 119 in binary equals to 1110111, and the number of bits equals to 7, and 7 minus 1 equals to 6. So then the value of I equals to 6. Okay, and the Miller algorithm says that you need to consider T equals to P, and P already was defined here, right? 4 and 73, and the value of F equals to 1. Okay. So the first steps of the Miller algorithm was not complex, just defining and determining the some variables. Now the algorithm, the Miller algorithm, starts and do some iteration. multiple iteration to finally compute the pairing. Okay, so the first round number one, the algorithm says that decrease the value of I by 1. So the value of I was 6 here. So I minus 1 equals to 5. And also it says that update the value of T and F, and we already updated these values. There is no new update. So then our updated value equals like the previous values here. Okay, so then the algorithm says that if the value of I is bigger or equals to 5, go down and follow this path. So here the value of I equals to 5, so then this condition is passed, and we need to compute S equals to 2 times of P, right? So 2 times of T, sorry. So the value of T equals to 4 and 73, and we want to compute 2 times of 73. And how we can compute this? So this is the scalar multiplication that we discussed in previous lecture, right? We can use from our website. Okay, so in our website, in multiplication over F sub P, and the default value are values that we need them. And so 2 times of, this is 2, and this is 4 and 73. So the result equals to 86 and 16. So 86 and 16, right? So then the computation is correct. Now let's follow the algorithm to compute the value, to update the value of f. Okay. Now we want to update the value of f. Oops. And yeah. So to update the value of f, we need to compute the f squared and then multiply by L sub TNT and L sub Sn minus S. Okay, what is this formula? So this is actually the formula of L sub TNP, L sub TNT, and L sub Sn minus S. So if you compare these three formula, so we need these three formula in our algorithm to compute this value. So this value, and later this value and this value, right? So we need this three formula to compute these values. And if you compare this formula to each other, you see that they are completely similar to each other. Just they replace the symbols. So for instance, if you replace the P here in this formula, everywhere that you see P just replace by T, you will reach by this formula, right? And if you replace T by S and the second T by minus S, you will reach to this formula, right? So these three formula are similar to each other. Okay, now we want to first compute L sub T and T. So we need to use from this formula, right? So let me erase these lines. Okay, so compute L sub T and T, we focus on this formula, and this formula says that if the value of T and T equals to each other, and it is equal to infinity. So definitely P equals to T, right? But here the value of T equals to 4 and 73, right? So then it is not infinity, it is not infinity, it is not infinity, right? So then the only remain part is this one, because T equals, definitely T equals to T. So therefore, we need to use from this formula to compute the value of T sub T and T. Okay, so we will write this formula here and then replace the value and then compute L sub T and T. So the formula says that L sub T and T equals to Y of Q. So, okay, so let me clean these lines. Okay, let me clean this, okay. Now we just want to replace the value in our formula. So the formula says that L sub T and T equals to Y, Y of Q, right? So this is the point of Q. So this is the X part and this is the Y part. So Y of Q equals this one. 6 plus 7I, right? Minus Y of T. So this is the point T, and this is the X value, and this is the Y value, right? So then minus 73 minus this formula. So 3 times X sub T to the power of 2. So again, this is the point T, and the X part of point T equals to 4, right? It's 4 to the power of 2 plus A. So what is A? A actually is the coefficient of X in the elliptic curve formula, right? We discussed it in previous lecture. So X, the coefficient of X here equals to 1. So then we replace A by 1 over 2 times of Y of T. Again, the point T is this one. The value of Y equals to 73, right? Again, multiply by this term. So this term says X of Q. So this is point of Q, right? And the first element is the X part. 92 plus 53 plus I. Minus X of T. Again, this is T. And the X part equals to 4, right? Now we need to compute this computation to finally reach to the value L sub T and T. Again, let me erase these lines and then discuss how we do this computation, this complex computation, right? Okay, to compute this computation, so this is just a simple multiplication and you need to compute 4 times 4 and then multiply by 3 plus 1 and then compute mod 101, right? You remember that all of the values uh, should be computed in mod p, which is 101. And then you multiply 2 times of 73, and when you multiply and then compute mod 101, you will see that the result equals to 45. So this part is also easy. So the imaginary part is just 7i. So we have 6 minus 73, right? Which is equals to minus 67. And it is 34 in mod 101. You can use from the website if you want to compute the mod, right? So let's use our website. Okay, so in our website, we had a part that allows us to compute mod. Okay, so in the modular arithmetic, we want to compute mod 101 over 101, and the value was minus 67. right? And it was 34, right? 34. So again, 92 minus 4 equals to 88. This is good. Now we need to compute this one. 49 divided by 45, right? How we can compute this? So you already remember that to compute this value, we can do this computation, right? We can do uh, this computation. 49 multiplied by 45 inverse, right? So what is 45 inverse? So let's use of the inverse, and this is 101 and 45, right? 45. So it is 9, right? So this is equals to 9. And then when you multiply these two value and then compute mod, you will reach the value of 73. You will reach to this value. Okay, so then you need to multiply this 73 by 88 and then 73 by 53 and then compute mod 101 and then add the imaginary part to each other and the real part to each other, and you will finally reach to this value. So then the value of L sub T and T equals to 10 plus 63i. Okay, so this part is computed. So now we want to compute this part, L sub S and minus S. And now let's see. To compute S sub S and minus S, we will use from this formula, and then we will use from let's see, from this formula, right? Why? Because the value of S equals to this one, 48 and 16, and the minus S, so the minus S equals to minus 1 multiplied by 48 and 16. So let's compute this value. So minus 1 multiply 48. So again, we use the computation over f sub p minus 1 multiplied by 48, 16. Right, the value equals to infinity, right? Okay, so here, okay, so the s is not infinity, but minus s equals to infinity, right? So then we have this situation. The s value is not infinity, and the minus s is infinity, so we will use from this formula. Sorry, I mentioned that we use from this formula. They are the same, but the condition is different, right? So since the minus s equals to infinity and s is not infinity, so we will use from this formula to compute L sub s and minus s. And this is the formula. It says x of q minus x of s. So what is x of q? Again, the point of q is defined here, and the first element is x, and the second element is y, right? So x of q equals to 92 plus 53 plus I minus x of s. So this is s, and this is the x value, which is 48. So then we have this part, and then 92 minus 48 equals to 44. Okay, so the value of L sub S and minus S is computed. So this one is computed and this one is computed. And now we want to update the value of F. So F equals to the original value of F, which is 1, right? So the original value of F was 1, right? To the power of 2 plus 10 plus 66i over 44 plus 53i. Okay, how we compute this value? So it's again, it would be 10 plus 66i multiply the inverse of this value, right? So you can use from the website and then to compute the inverse. Okay, let's see in the website. The computation over extension. Extension field. You want to compute the inverse, right? So the inverse of 44 and 53 equals to 44 and 84, right? 44 and 84. Now we want to compute the multiplication of these two values. Okay, so we have the multiplication tool here. So 44 and 84 multiplied by 1066. 1066, and the result equals to 58 plus 60i. 58 plus 60i, right? Okay, so the value of F is updated now. Okay, so let's follow the algorithm. The algorithm now says that set the value of t equals to s. So the value of s is this one. So then the value of t equals to 84 and 16. And now it says that if the sorry, this is not n, this is not L, this is n. If the bit number I of the n equals to 1 or 0, we want to check this. So now the value of I equals to 6, right? Sorry, 5, right? So we want to see what is the fifth bits of the I, the n subbinary. So this is 0, this is 0, this is 1, this is 2, this is 3, this is 4, and this is 5, right? So the 5th bit of n subbinary equals to 1. So since it is 1, we need to go down and follow this step. So this step says that set the value of s equals to t plus p. So this is the value of t, and this is the value of p, right? The value of p is not changed. So 48 and 16 plus 4 and 73. We need to compute the addition of these 2 points. Again, we use our website. So let's use our website. So this addition should be in over FP. Okay, to addition of 2 points, 48 and 16. 48 and 16. 4 and 73. So the result equals to 15 and 83, right? 50, 50 and 83, right? So then this addition is also computed correctly. Okay, Now we want to update the value of f again using a similar formula, but the difference from the previous formula is that we don't have any squared value here. So it is equals to f multiplied by L sub T and P and L sub S and minus S. So again, to compute L sub T and P, we need to look at the formula of S. Yeah, this is L sub T and P, right? And so this formula is accepted, right? Why? Because 2 point T and P, they are not equals to each other, right? So this is point T and this is point P. So definitely they are not equal to each other, and T is not infinity, P is not infinity. So the x of 2 point also is not equal to each other because the x value of T equals to 48 and the x value of P equals to 4. So the only situation that is passed is this one. 2 point, they are not equal to each other and their x value are not equal to each other. So then we use from this formula to compute L sub T and P. So to compute this value, again, you need to replace the values in the formula. What is the value of y of q? So this was q, right? And this was the value of x, and this value was the value of y, right? So if you replace all of these values and then compute similar to previous discussion in here in this formula, you will reach to this value. Okay, similarly with the same discussion, you need to compute L sub S and minus S by this formula, and then if you do the computation, you will reach to this formula, and then we want to update the value of F. So the value of F equals to the previous value of F, so which is this one, right? 58 plus 60, 64. Right? Multiply by L sub T and P, which is this one, over the 42 and 53, right? Okay. How can we do this computation? You need to multiply this value by the inverse of this value, right? So first we want to compute the inverse of this one. So let's use the website and do this computation, for example, and then the next computation would be the same. Okay, so the inverse in the extension field, we want to compute the inverse, right? What was the value? 4253. So the inverse equals to 95 plus 10, right? 95 plus 10. Now we want to multiply the three values to each other, right? First, let's to multiply 58. So we use from here for the multiplication, 58 and 64. Multiply by 47 and 55, right? So the result equals to this. 29 plus 78. So the multiplication of these two values equals to 29 plus 78, and it should be multiplied by this one, 95 plus 10, right? By this one. Now we want to multiply these two values to each other, right? So let's compute this multiplication. So this is 29 and 78 multiplied by 95 and 10. So then the final result equals to 84 plus 13. 84 plus 13, right? Now the final update of the value of f is this round is done. Now the final step says that t equals to s, so the value of s equals to 50. So here, the final value of s equals to 50 and 83. So we update the value of t into this value. Okay, so from this round, we have the value of t and f that should be updated for the next round, right? Because at the first step of each iteration, we need to update the value of t and f. So this value should be updated by these ones for the next round, not this one. This iteration is done. For the next iteration, the value of t and f would be updated. And now, yeah, this is the updated value for t and f, right? Okay. So again, we follow the algorithm similar to the previous iteration, decrease the value of I by 1. So the value of I was 5 in previous iteration, and now it is 4. And since the value of I equals or higher than 0, we go down. So again, value of s equals to 2 times of t. You will use from the website to compute this value to ensure that this is correct. And then with a similar discussion to update the value of f, we need to compute L sub t and t, and then L sub s and minus s, and then update the value of f by this computation, right? The value of f to the power of 2. So this is the value of f to the power of 2 we are using from this formula, right? Multiply by L sub t and t, which is this value, 5 plus 72 over the L sub s and minus s. So again, you compute the inverse of this value using the formula, and then you multiply it by this one and this one, and this one actually is the square value of 84 plus 30i, right? So this means that first you need to compute 84 plus 13i multiplied by 84 plus 30i. Okay, so after this computation, you will see the updated value of f is this one. Again, you equals the value of t by s. And now you need to see that if what is the value of n? Again, this is n sub binary of 4, right? So again, we want to start and count 0, 1, 2, 3, 4. So the fourth bit equals to 1, right? So since the fourth bit equals to 1, we go down, s equals to t plus p, and then again we use the same formula to compute L sub t and p, L sub s and minus s, and then update the value of f, and then update the value of t. So we have these two values for f and t for the next round. Round 3, yeah, we have the values for t and f, right? Now again, in round 3, we want to decrease the value of I by 1. It is equals to 3. And since 3 is higher than 0, we go down and compute s 2 times of t with the same formula. We update the value of f and then update the value of t. Okay. Now we want to see what is the n subbinary of 3. Okay. So let's start again. We count from right. 0, 1, 2, 3, right? So the third, the bit number 3 equals to 3, right? So since it is not equals to 1, so we do not follow and go down. We go back and start the next iteration. So that's the reason we don't have any computation here for the value of s and value of f and the value of t, right? So now we just have the value of t here and f here that should be considered as the update for the next round. Okay, at the next round, we have the same thing. We decrease the value of I by 2, and then the updated value of t and f from previous iteration, and then compute the value of s, f, and t, and then again, the bit number 2 equals to 1. So 0, 1, and 2. Bit number 2 equals to 1. So now we need to follow and go down. So next iteration is the same. And now this is the final iteration. Okay, so round number 6. So here the value of I equals to 0. And again, since the I equals to 0, we go down. We update the value of S by this formula, the value of F by this formula, and T, and also since the bit number 0, this one, right, equals to 1, we go down. Okay, now we have a different situation in round number 6, and then you will see that the formula to compute f would be a little changed. Okay, the algorithm says that you need to compute t plus p. So this is the value of t, and this is the value of p. And so let's use our website to compute this addition, 4 and 28. So the addition in the elliptic curve and here. So the addition 4 and 28, 4 and 7, 3. So the result equals infinity, right? Okay. So what happens if the result for S equals to infinity? Now we want to compute the value of L sub t and p, right? So let me see here. Okay, to compute the value of f, we need to compute L sub t and p. And now we want to reach out to the formula of t and p and see which one we need to follow. So here, this is point t, and this is point p, right? So definitely none of these 2 points equals infinity, right? So this is not infinity, this is not infinity, and this is not infinity, right? So 2 point t and p, they are not equals to each other, okay? This is past. And also the x part of t and p should be equal to each other, right? So the x part of p equals to 4, and the x part of t also equals to 4, right? So that's the reason for this round, we do not use from this formula like the previous round. Or sorry, in previous round, I think that, yeah, we use from this one. So now we need to use from this formula to compute L sub t and t, right? So L sub t and t equals to x of q minus x of t. X of q is this value, and x of t equals to 4. You see, we have different situations, so then the formula to compute L sub t and p would be changed. So the formula for L sub s and minus s, so now we need to check this one, right? Okay, so the value of s equals to infinity, and also the minus s also is infinity. So this situation is passed, and then the L sub s and minus s equals to 1. Why? Because the value of s is infinity, and also minus 1 multiplied by infinity also equals to infinity. Okay, so these two values are computed. Now we want to update the value of f. And this update and computation is easier than previous iteration, and the value of f equals to 31 plus 80, 81. And then the final value of the final step, t equals to s, and since s equals to infinity, t would be infinity. Okay, we go for the next round, round number 7. So we update the value of t and f, and then now we update the value of I by -1, right? So now we check this condition, and we see that the value of I is not higher or equals to 0. So then this condition is not passed, and we don't need to go down, and then done. We finally finish the Miller algorithm, and now we reach to this value. So the value of f equals to 31 plus 81i. Okay, now we want to compute the pairing of these 2 points. So we have given these 2 values, these 2 elements to the Miller algorithm. Now we have reached, after following the Miller algorithm, we have reached to this value for f. And this f is actually f of f sub p and q based on the formula that we have defined already. So now we need to compute this value to the power of p minus 1 over 2 to reach to the value of thought pairing, right? We already mentioned that there are multiple pairing functions, and 2 well-known of them are Tate pairing or thought pairing and Weil pairing. So the formula of Tate pairing equals to the f to the power of p minus 1 over 2. So let's replace it. Sorry, this should be Tate, right? So this should be Tate by mistake. So it is equals to the value of f, 31 plus 80, 81, I to the power of, what was the value of p? It was 101, right? 101 minus 1 equals to 100 over 2 equals to 50. Now we want to compute 31 plus 81 to the power of 50. So again, let's use our website. So in the extension feed, we have exponentiation, right? So to the power of 50, and then 3181. So it is equals to 67 plus 61, right? 67 plus 61. Okay, so this was the algorithm to compute the value of f and then compute the Tate pairing. So we use the same algorithm, the Miller algorithm, to compute f sub p and q. So we already mentioned that the value of f, p, and q is this value, the value that we computed from the Miller algorithm. Now we need to, for the Weil pairing, we need to compute f sub p and f sub q and p. So this means that in all the, we need to repeat the Miller algorithm again, but we already need to replace the value of f and q in all formulation, right? So this means that, for instance, in the formula of t and p, it should be in this form, L sub t and q of p, right? And then replace q here by p and p by q, and again here by q, and here by Q, all of this formula here by Q, here by P, here by P, right? And also in this formula, so here by P, here by P, okay, on this one by Q, and this one by P. So yeah, so the whole iteration of the Miller algorithm should be repeated again when we replace the value of P and Q to each other. And the final result for the F value would be F sub Q and P, right? So since the computation is similar, we don't want to compute and follow the algorithm, but we already have done this computation and we saw that the final updated F equals to 40 for the I, right? Okay, now we want to compute the Weil pairing, minus 1 to the power of n. So the value of n was equals to 119, right? So the value of n equals to 119. So minus 1 to the power of 119 equals to minus 1, right? And then 31 plus 81 I multiplied by the inverse of minus 114. So this minus 1 is from this part, minus 1 to the power of 119. So again, use the website to compute the inverse of this value and then multiply by this value, and then you will see that the Weil pairing of these 2 points equals to 98 plus 48I, right? So these examples show that it depends that what kind of pairing we are using to do the computation. For the 2 elements, we computed both Weil pairing and Tate pairing, and we see that so they result they are not equal to each other. But the Miller algorithm that is the main part of the computation is the same. Okay. Okay, now in our website also we have a tool that allows you to compute the Weil pairing. Okay, so here. So why just Weil pairing? Because for our example for gross 16, we have used from Weil pairing. Because when we are try to design the example, it was easier to fix everything to work by Weil pairing. Okay, in the Weil pairing, it says that the curve already is defined, and this is the element of group 2, and this is the element of group 1. You take one element from group 1 and one element from group 2, and then compute the pairing, right? The pairing of 4 and 73, and this value equals to 98 plus 40i, right? This is actually the default value in the website is actually the value that we computed in the PowerPoint. Yeah, this one. Okay, so finally we have finished the discussion about the algorithm of computed the pairing, right? Now we want to go back to our discussion again. So what was pairing? It was a function that take one element from group G1 and one element from group G2 and then do some computation, and results would be an element from group T, the group target, and you saw that the result actually was an element from the group, the target group, right? However, we mentioned that not all the function is considered as a pairing. The function should satisfy multiple properties. So the first one is this, Okay, what is this property? It says that if you take 2 elements from group G1, right? So if you take 2 elements from group G1 and another element from group G2, and then compute the pairing of them, it should be equals to the pairing of the first element multiplied by the pairing of the second element by the element of the group 2. Okay, so now we want to see with an example that if this property is correct or not. Okay, let's consider an example. We say that let's consider point P equals to 38 and 50, right? So this is point P. And point Q equals to 55 and 30, right? So this is point Q. And point T equals to 20 and 10 plus 96 and I, right? So this is point T. So the formula says that if you compute the left side and if you compute the right side, the result should be the same. So first we want to compute the left side. So the left side says that the pairing of P plus Q and T. So this means that the pairing of 38 and 50 plus 55 and 30, right? And 20 and 10 plus 96. So first we need to compute the addition of these 2 points, 38 and 50, 55 and 30. So, okay, so let's use the website to compute this addition. So again, we want to go for the elliptic curve and then over the FP to compute the addition, right? So the addition of 38 and 50 and the 55 and 30. So the addition equals to 66 and 78. So 66 and 78, right? Okay, now we have computed, Now we have computed 60, the addition of these 2 points. So we'll replace the addition by 66 and 78. And now we want to compute the pairing of these 2 elements. So we don't want to follow the Miller algorithm. We will use from our website. Okay, so let's see. So in our website, in the Veil pairing, we want to put this value here, 66, 78, 10, so 20, yeah, 20, 0, 10, 96. Okay, result equals to 88 plus 53, right? 88 plus 53. So this is the left side, right? The pairing of P plus Q and T. So this was the left side. So the right side says that you don't need to add these 2 elements to each other. You need to compute the pairing of any of both of these 2 elements by T, right? So this is the formula. Compute P pairing of P and T, and then compute pairing of Q and T. Okay, so let's compute pairing of P and T. So the value of P equals to 38 and 50, and the value of T is given here, right? Okay, so again, use the website to compute pairing. So the pairing of 38 and 50. 38 and 50. So this is the value of T, and the pairing equals to 55 plus 19, right? 55 plus 19. So the other term says that compute pairing of Q and T. What is the value of Q? So the value of Q equals to 55 and 30. So 55 and 30, and the pairing equals to 57 and 41. 57, and 41. Now we want to multiply these two values to each other. Okay, use the website for the extension field and then for multiplication. So the value equals to 5919 multiplied by 5741 equals to 88 plus 53, right? So the multiplication equals to 88 plus 53, right? So this means that the first property is passed. So we saw that the pairing, the veil pairing that is computed by the Miller algorithm is a complex function that is guaranteed that this property is correct. So you can do the same thing to check that, to ensure that the second property also is correct, right? So for the second property, instead of taking two elements from the group one, the first element is from group one. The second two elements are given from group G2. So now the left side equals to pairing of this one and the addition of these two. First, you need to compute the addition of these two elements. Use the website to compute the addition, and you will see that the addition should be equals to this one, right? Okay, so let me show which part of the website you need to use. So yeah, here in the extension field for the addition. In the addition, you can add these two elements to each other and you will see the result is this one. And then compute the pairing of these two elements. Next, compute these two and compute these two and multiply these two elements to each other. And you will see that the results would be equal to each other. Okay, now we see that our function that we have discussed passed the two conditions. The third condition says that the function should guarantee the non-degeneracy. So this means that if you take the two elements from group G1, their pairing should not be equals to 1. So we have simplified the formula of pairing and in our website, it just computes the pairing when the first element is given from G1 and the second element is given from G2. But the general formula of pairing could take both elements from the same group. So, however, without any explanation or example, just accept me that the veil pairing and Tate pairing, they guarantee this property also. Okay, the final property is computationally efficient. So, yeah, we already discussed the veil pairing and reviewed the veil pairing, and you'll notice that this algorithm is not so complex, right? It is computationally efficient. So why this matter? Because finding a valid pairing function, it was very, very complex. For many years, scientists tried to design such a function that guaranteed this property, but the original function, they will not be computationally efficient. But now we see that the Tate pairing and veil pairing, they are efficient. Okay, so we discussed this property, and now based on this property, we want to say that a pairing function also guarantees this list of properties. So we can conclude these properties from these two properties. The first one, we want to prove the first one, and then you will later can rehearse to prove the second and the third one. For the first one, so we already say that the pairing of we know that the pairing of P and Q and T equals to pairing of P multiply pairing of Q and T, right? Now we have NP here, and NP equals to P plus P plus P plus P n times, right? So then we can consider this one as P and this n minus 1 times as Q, right? So then based on this formula, we can disjoint the first one and the remaining part. So we can disjoint this one from this part. Again, you have n minus 1 times of P, and you can disjoint from this list over here. And if you continue this process, you will see that the pairing of NP and Q equals to pairing of P and Q n times multiplied to each other, right? N times. And so this means that pairing of P and Q to the power of n, right? So the other property is the same thing for M, which when M is here, and you will follow the same formula to prove by this one. And the third one also would be proved by the second and these by the first and second. So we will use from this proof in our next lecture when we want to design a ZKP system. Okay, done. Our pairing discussion is almost done. Now we just want to discuss about the pairing-friendly elliptic curve. So we already mentioned that designing a pairing function was not easy. So it took many years to reach to efficient algorithm. And so other than the algorithm to compute pairing, it also matters what is the formula for the elliptic curve. So not all of the elliptic curve, they are easy to compute the pairing. So for some elliptic curves, the computation of pairing is not efficient or it's not secure. So that's the reason we have a concept of pairing-friendly elliptic curves. So for instance, BLS 12-381 is an elliptic curve with this formula. This is a pairing-friendly elliptic curve. So this means that if you took this curve, consider this curve to generate your group, so then the computation of pairing would be secure and efficient. So the other well-known pairing-friendly elliptic curve is this one, BN248, which the formula is this one, when the value of B is this big value, and also the value of P is this one, right? Okay, so these are the pairing-friendly elliptic curves, but you remember that for our computation, we'll use from the formula y to the power of 2 equals to x to the power of 3 plus x plus 9, which is not a pairing-friendly elliptic curve, but for our small value of prime, it is efficient, and we just use it to understand the concepts. Okay, thank you. In next lecture, we'll discuss how we want to use pairing to design a ZKP system. Thanks.